All right, so today is Friday, and we're going to be going over lesson 4, which is more drawing of um, Lewis models or like molecules. But we're going to add a little bit of a wrinkle to it. We are going to add expanded octets and electron deficient molecules, but we're also going to draw molecules that are just a little bit more complicated than the ones we did in class yesterday. So let's just kind of get into it. The rules for everything that we're going to do today are still pretty much the same. So I don't think we need to review much of that, but we are going to start by talking about how to draw a structure that doesn't have one obvious central atom. So here we have C2H4, and in C2H4, there are two carbons and 4 hydrogens, and because there's 2 carbons and 4 hydrogens, that puts us in a situation where we can't really readily identify what the central atom is. So the easiest way to do that is to simply look at what we've been given and remember that when carbon is present, carbon is almost always in the center. So I'm going to start by taking my carbons and putting them next to each other. Oh, actually, I lied. I should probably figure out how many electrons I'm working with first. So let's start there. So I have carbon, and there's 2 of them. And according to the periodic table, carbon has 4 valence electrons, so that's 8 valence electrons. There is hydrogen, and there's 4 of them in the formula. And hydrogen has 1 valence electron according to the periodic table. So 4 times 1 is 4 valence electrons. So I'm going to add all that up, and 8 and 4 is 12 valence electrons total. Now what I'm going to do is I'm going to go ahead and grab the carbons and put them in the middle. So I'm going to put a carbon here, and I'm going to put a carbon here. And so to the carbons, I'm going to bond them together first. So I'm going to add a bond. Then I'm going to spread my hydrogens out. And I know that some of you are thinking to yourselves, well, we could do this and then like this. But the problem with that is that's not really super lopsided. That's actually pretty lopsided. And to be honest, nature likes to be more symmetrical than not. So what I'm going to do is I'm going to try to, since I have an even number of hydrogens, I'm going to put 2 hydrogens on one carbon and 2 hydrogens on the other carbon, trying to make as much symmetry as I can. The next thing I'm going to do is I'm going to go and bond those hydrogens to the carbons, like so. And now I'm going to look at the number of carbons that I have, or number of bonds that I've used. So I've used 1 bond in between the 2 carbons, and 1 bond in between the carbon and each of the hydrogens. So I've used a total of 5 bonds. So if I take my 12 total electrons, and I know that I've used 5 times 2, which is 10 electrons, that leaves me with 2 valence electrons to find a home for. Now, the issue is that I have to remember that hydrogen is that special atom that only needs 2 electrons. So each of the hydrogens is participating in 1 bond, and if each of the hydrogens is participating in 1 bond, it has 2 electrons. So all of my hydrogens are satisfied. The only thing that's not satisfied is either of my carbons, because the carbon on the right-hand side has 3 lines or 3 bonds, so 2, 4, 6 electrons, and the carbon on the left side has 3 lines or 3 bonds or 2, 4, 6 electrons. So neither of them are satisfied. So how can I use 2 electrons to make all of my atoms satisfied or have 8 valence electrons? Well, the answer here is I'm going to use those remaining 2 electrons and make a double bond here. Now if I look at my carbons, the carbon on the right has 1 bond with hydrogen, another bond with hydrogen, and 2 bonds with the other carbon, 2, 4, 6, 8. And the carbon on the left is the exact same thing. So now each atom has all 8 electrons, or each atom has its most stable arrangement of electrons, and everything is good. So now I need to go ahead and identify the type of polarity or what type of bond I have present here. So I have 2 types of bonds. I have a carbon-carbon bond, and I have, a carbon, and I have 4 technically carbon-hydrogen bonds. So if I go to my periodic table, on my periodic table I see that carbon is a 2.5 and hydrogen is a 2.1. So I'm going to remember that. So with my carbons, it's a 2.1, or I'm sorry, 2.5 minus 2.5. And so that gives me 0.0, which tells me it is a non-polar covalent bond. And so that's my carbon-carbon. And my carbon-hydrogen, as we might remember, was carbon was 2.5 and hydrogen, I should go check. Oh, yep, it was 2.1. It was 2.1. So 2.5 minus 2.1 still equals 0.4. So that is a non-polar covalent bond as well. And so what that tells me is that for this structure, I don't have to draw any arrows and I don't have to do any partial charges, and I'm left with that particular structure. Now, that was kind of easy. So now we're going to go on to one that's a little bit more complicated. So here we have CH3OH. And there's a lot of things going on here. But one of the things that's kind of important to think about here is what is actually what is the central atom and what's attached to the central atom and what might not be attached to the central atom. And that's kind of the fun thing about some of these covalent compounds, is that there are, like, the way that they're written is kind of how they sort of look. So here I see that I have one carbon, I've got three hydrogens, one oxygen, and another hydrogen. Okay, so that one carbon, because it's first, because there's only one of them, because it's carbon, is chances are that one's going to be my central atom. So I'm going to figure that out in a second, but I have got to figure out how many electrons I have to work with. So carbon, there's one of them, times carbon's 4 valence electrons. So 4 valence electrons. Oops. I also have, I can group the hydrogens together, but with these types of molecules, I'm going to actually keep them separated. So I have 3 hydrogens times 1 valence electron for 3 valence electrons. I have 1 oxygen times 6 valence electrons for 6 valence electrons, and then I've got 1 more hydrogen. This one I am keeping separated, and I'm going to try to show why in a couple of moments. So now when I add all this together, 4 and 3 is 7, plus 6 is 13, plus 1 is 14 valence electrons. So I'm going to start with carbon as my central atom. So here it is, carbon. And I'm going to read the compound from left to right. So carbon has 3 hydrogens, 1 oxygen, and then there's another oxygen. So what that tells me is that to the carbon for sure, 3 of those hydrogens are bonded directly to it. And then there's an oxygen. So that's CH3 and then O. So what that also tells me is that my oxygen is bonded to the carbon, but it's also bonded to that remaining hydrogen. And some of this is going to come with a little bit of practice, but for the most part, that's kind of what we need to think about. Is read the formula from left to right and draw it as best you can based on how it looks. So now I've got to go ahead and figure out how many single bonds I used. So around the carbon, there are 4 bonds: carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, carbon, oxygen. And then after the oxygen, there's an oxygen, hydrogen. So I've used 10. So I've used 2, 4, 6, 8, 10. So I'm going to put this up here So the 14 valence electrons minus 10 for each of the lines leaves me with 4 valence electrons to find a home for. So if I start with my central atom, carbon has 4 valence or 4 lines around it. Each line is worth 2 electrons, so 2, 4, 6, 8. So carbon has 8 valence electrons. It's in good shape. Each hydrogen is participating in one bond. One bond is 2 electrons, and that's the number of electrons that hydrogen needs. So hydrogen's in good shape. Now the oxygen right now is only participating in 2 bonds, 1, 2, 2, 4. So it needs 4 more electrons. And good thing we have 4 more electrons in our bank, so 2, 4. And this is what our structure looks like. And I realized that, like, looking at what the structure formula was versus what it looks like, hopefully you can see that it kind of looks similar-ish in terms of, like, going from left to right. Now, the last thing we have to do is we have to identify the type of bonds that are present. So I'm going to go through and do the same process that we've been doing. So I have carbon and hydrogen, and I have, looks like I'm going to have carbon and oxygen. And then this structure also has oxygen and hydrogen. So I'm going to go to the periodic table and figure out what the electronegativities are. So here it says that carbon is 2.5, oxygen is 3.5, and hydrogen is 2.1. So I'm going to try to remember those. I'll probably forget and have to come back and check anyway. So we said carbon was 2.5. So let's do this one. So carbon is 2.5. I remember that hydrogen is 2.1. So that tells me that 2.5 minus 2.1 is 0.4, which tells me I have a non-polar covalent bond. And I like that because that means I don't have much more to do for that particular bond. All right, let's take a look at carbon and oxygen. Okay, so I can remember because I don't have to remember. I can see it. It's carbon is 2.5. Like, man, I can't remember what oxygen is off the top of my head, so I got to go check. Oh, it's 3.5. So oxygen is 3.5. And 2.5 minus 3.5 is 1.0. So that is a polar covalent bond. All right, so that means I got to do something there, and we'll deal with that in a minute. And then the last one is oxygen and hydrogen. This good thing I don't have to go back and check my periodic table because I do see that I have the numbers here. So oxygen was 3.5, hydrogen was 2.1. And when I subtract those, I get a value about 1.4. So that also is a polar covalent bond. Okay? Now, with the polar covalent bonds, we have to draw an arrow and a dipole arrow, and we have to do partial charges. So, as you may recall, we draw the arrow towards the more electronegative element. So that means that in the carbon-oxygen bond, the arrow is going to go towards oxygen. So I'm going to draw that here. The carbon-oxygen bond goes towards oxygen. And in the oxygen-hydrogen bond, the arrow is going to go towards hydrogen. So I have to draw this, or towards oxygen, rather. I misspoke. Now, the other thing that you might remember is that the partial charges, right, delta plus meant, or I'm sorry, delta plus and delta minus. Delta minus meant towards, words are hard to, W-A-R-D-S, and delta positive meant away. So in terms of this one, the hydrogen is going to be delta positive, and the oxygen is going to be delta negative, and the carbon is going to also be delta positive. So here we have our structure where part of it is nonpolar, part of it is polar, and we had to represent that in both cases. All right, moving right along, we now need to go talk about something called electron deficient or expanded octets. So we've already talked about how atoms can be electron deficient. And what we mean by that is that they don't need 8 valence electrons to be their most stable arrangement of electrons. And there's really 3 that we're going to focus on. And to kind of refresh your memory, we had hydrogen, which needs 2 electrons. So I'm going to do this. Element, electrons needed, and bonds. Okay, so hydrogen needs 2 electrons, so it does that by participating in 1 bond. Beryllium needs 4 electrons, and it does that by participating in 2 bonds. And then lastly, boron needs 6 electrons, and it does that by participating in 3 bonds. The expanded octet, though, is, and I'm gonna jump over to the periodic table to show you in a minute, is when we start drawing structures that have elements from the D block that sort of get involved. So what I mean by that is we have elements that are after, well, let me go over here. So just to refresh your memory, this is your D block. Okay, so this is the D block. Why does that not do what I want to do? Let's try that. Okay, sideways. All right, well, shoot. Oh, okay, that worked. That's weird. Okay, well, it's not doing what I want. Okay, well, all right, well, then we'll draw. We'll draw it. We'll draw it. We'll draw it. Okay, so this is our D block from here to here to here to here. So everything in here is a D block, but it's also a metal. So these are elements that basically occur in these are elements that basically occur in the 3rd energy level or the 3rd period and beyond. So we're talking about elements over here and over here and over here and over here. Those are the nonmetals that are in the third period and beyond. And the reason why it's important is because a lot of them have electron configurations that dabble in the D block. And when they dabble in the D block, what ends up happening is that there's a lot more space for electrons to kind of hide out. And when they hide out in that lot more space, what ends up happens is that we can add more electrons. So, or we can add more bonds than we should. So an expanded octet occurs with atoms that are nonmetals in the 3rd period of the periodic table and beyond. So the 3rd period, the 4th period, the 5th period, the 6th period, etc. And the reason for this is because the D sublevel is really big. And allows for electron I want to say movement. And it's not really what it is, but it's kind of the best way I can come up with to describe it in simple terms. So it kind of allows for electrons to kind of move or hide or something along those lines. Now, Let's do a couple of examples. So here we have BeF2. BeF2 falls into one of the categories of an electron deficient atom. So we're going to start by doing what we do, which is identifying the number of electrons. So beryllium, there's one of them. And beryllium, according to what we just talked about, has a total of 2 valence electrons. So 2 valence electrons. And fluorine fluorine, and we have 2 of them, has 7 valence electrons, which 2 times 7 is 14 valence electrons. So we add all that up and we get 16 valence electrons we need to find the home for. Central atom is the element that is generally by itself, or there's only one of them, or it's the first one in the formula. So that's going to be Be in this case. Fluorine, I'm going to place one fluorine on one side and another fluorine on the other side, and I'm going to connect them with a bond. At this point, 16 valence electrons minus 2 bonds, which is 4, leaves me with 12 valence electrons to find a home for. So 16 minus 4 is 12. Now I'm going to start placing electrons around the atoms that are left. But before I do that, I should do a quick check on my central atom because it's one of the electron deficient. So my central atom is beryllium and it needs 4 electrons. It has 2 bonds with 2 electrons each, so 2, 4. So I don't want to add any electrons to beryllium at this point because beryllium has got all the electrons it can handle. So I'm going to start placing pairs of electrons, 2, 4, 6, 8, 10, 12. And so now my fluorine has 6 dots, which is 6 electrons, and 1 dash, which is 2 electrons, so that's 8, and that happens on both sides of them, so everything is good. Now I need to go ahead and identify whether or not I have to draw arrows. So I'm going to be looking at the relationship between Be, beryllium, and fluorine. I'm going to go to my periodic table and see that fluorine has an electronegativity of 4 and Be has an electronegativity of 1.5. So let's see, that's going to be 1.5 minus 4.0, which is going to be really, really big, which is going to basically be polar. Its electronegativity is 2.5. So that makes this a polar covalent set of bonds. So if that's the case, that means I have to draw some arrows. So here I'm going to draw an arrow pointing toward the more electronegative element. And since there's 2 bonds that are identical, I'm going to draw them like this. And then I have to use my partial charges. And remember, the delta positive is where the electrons are being pulled away from, and the delta negative is where the electrons are being pulled towards. So that means each fluorine is going to be delta negative, and the beryllium is going to be delta positive. Cool. Now, there's 2 more examples, and these are a little bit more complicated because these are going to be expanded octets. I'm just telling you that ahead of time. So let's kind of jump into it. Let's go there. So I've got phosphorus, PeCl5. So I have phosphorus. I've got one of them. Phosphorus has 5 valence electrons. Chlorine. I happen to have 5 of them. And chlorine has 7 valence electrons. 5 times 7 is 35 valence electrons. Add that up, it's a total of 40 valence electrons that we have to find a home for. So I'm going to take my central atom, which is phosphorus. It's the first atom. There's only one of them. And I'm going to place it right in the middle. And now I've got my chlorines, and I'm going to attach all of my chlorines to my phosphorus. So it's going to look something like this. Okay, and I'm going to attach them with a single bond. So 2, 4, 6, 8, 10. So 40 valence electrons minus 10 leaves me with 30 valence electrons to find a home for. Now, here's the thing. Phosphorus is in the third period. So phosphorus is in that third period. So we can start, so these are atoms that have the ability to have an expanded octet. They don't always have an expanded octet, but they have the ability to. So that's why phosphorus will allow there to be 5 atoms of chlorine attached to it. So phosphorus, even though it has 10 electrons around it, that's going to be okay. Because what we're really looking for here is, did we use all of our electrons? So I'm going to start placing pairs of electrons around each chlorine at this point. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So I've used all my electrons. Each of my chlorines has 6 dots and 1 line, so that's 8 electrons. So everything is good. Now, I'm going to go ahead and check my electronegativity difference. So phosphorus, let's see, phosphorus has an electronegativity of 2.1. Chlorine has an electronegativity of 3.0. So I've got phosphorus, I've got phosphorus, and I've got chlorine. And we said that phosphorus was 2.1. And chlorine is 3.0. So 2.1 minus 3.0 is 0.9. So that tells me that it's going to be silly. That's going to be polar, covalent bond, which means that I got to draw arrows. And I got to draw arrows toward the more electronegative element. So every one of these gets a line out, or an arrow out. And like so. And then we have to draw our partial charges. And remember that delta negative is where the electrons are being pulled toward. And so in this case, all of the chlorines are going to get a delta negative. And the phosphorus is going to be delta positive. That's that. All right, one more to go. Xenon XeF6. Okay. So in this case, I have my central atom is going to be xenon. It's going to be xenon because there's only one of them, and it comes first. So xenon has 8 valence electrons to bring, which is crazy. We have fluorine, and fluorine, there's 6 of them times 7 valence electrons, and that's 32 valence electrons. Nope, I lied. It's 42 because I can multiply. Jeepers, creepers. So when I add that up, that becomes 50 valence electrons. Okay, so now what we're going to do is we are going to go and we're going to go ahead and place our central atom. So xenon, I'm going to go right here in the middle, and I'm going to place my 6 fluorines around. So 1, 2, 3, 4, 5, 6. Well, that is not nice. I don't like the way that looks. I'm going to try to spread them out a little bit more because that was kind of gross. So here we go. 1, 2, 3, 4. That's better. 5, 6. And I'm going to draw a single bond for every single one of them. That's 2, 4, 6, 8, 10, 12. Ooh, why am I drawing that bond to? That doesn't make sense. 10, 12. Okay, so 50 valence electrons minus 12, what is that, 38 valence electrons we still have to find a home for. So I'm going to start adding electrons. So it's going to go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. Now, here's the issue. Because xenon is an element that can have an expanded octet, there are rules, but for the scope of this class, there's kind of no rules to how many electrons it can have around it. So we're going to just say that we're going to take that last electron, the last set of electrons, and just throw it right there. So now xenon has 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 12 bonds, or 12 electrons and 6 bonds, and 2 more electrons. So it's got 14 electrons around it, which is crazy, but that's the way that it is. And then each of the fluorines has 6 electrons and 1 bond, so they have a total of 8 valence electrons, so everything there is good. So now we're going to go ahead and identify what type of bond this is. So I have xenon, and I have fluorine. So I'm going to go to my periodic table, and I'm going to see that fluorine has an electronegativity of 4.0, xenon is 2.6, so 2.6, oops, well, 4.0 and 2.6. So 2.6 minus 4.0 is 1.4, which tells me it's a polar covalent bond. Polar covalent bond. And so if it's a polar covalent bond, we have to draw the dipole arrow. We have to then do that for every single one of them. So that's going to look something like this. Looks something like this. That's ugly. Okay. And then we have to draw our partial charges. Our partial charges, the more negative element, the negative side is where we get the delta negative. So that means that fluorine is going to be, all of these are going to have delta negative. And the xenon is going to be super delta positive. So I'm going to put that right there. Okay, so that is the lesson on electron deficient or expanded octets and structures that are just a little bit less symmetrical than what we're used to. All right, if you have any questions, let me know, let your teacher know, and good luck with your homework this weekend.